All right, so welcome everyone. This is our second student research presentation session. Glad to have you all joining today. Um, through a happy circumstance, all of the presenters today are from the University of Nebraska, one from the Lincoln campus and 4 from the Omaha campus. So great to have you all joining. We are going to hear about a variety of different projects that you're working on, I think all in the sort of bridge infrastructure, bridge cyber infrastructure kind of space, which is a sort of longstanding area that the Hub has been engaged in through the Spoke Award that was awarded several years ago. So glad to see Robin Gandhi on the call, who is one of the co-leads of that work. There was a recent follow-on award made to that very recently, so congratulations with that award. And we're glad to have some of the students engaged in that project joining us today as well. So we're going to start with Akshay Kale.
Hello, everyone. I am Akshay. I'm a PhD student at University of Nebraska at Omaha. And my research is primarily focused on developing methods for explaining complex machine learning algorithms. So in this presentation, I intend to share some of my research on developing methods for understanding bridge deterioration and bridge maintenances. So just to give you a background, United States have over 600,000 bridges, and over 4 out of 10 bridges are above the age of 48, and the design life of a bridge is just 50 years. So these bridges are very old. The 9.1% of the US bridges are structurally deficient. And to maintain these bridges and to rehabilitate them, it will require around $123 billion in bridge rehabilitation. So clearly, we have lack of resources and we have lack of time. So my research tries to address these questions by using a lot of data to kind of model these bridge maintenances so that we can predict the future maintenance by learning the current maintenance patterns. And by that, we can probably give attention to the bridges that require the most attention. And with that, we can also learn about influential variables that contribute to deterioration or are helpful in understanding maintenances, and how these influential variables kind of interact with each other and what the patterns are. So the data that we are working with is called an inspection record. So every bridge is inspected every 2 years. And so there are over 600,000 bridges. So we have over 17 million records altogether from 50 states and from year 1992 to 2020. And these inspection records altogether is called a National Bridge Inventory, which is hosted by Federal Highway Administration. And in addition to that, we also use external data because we want to account for weather patterns. We want to account for geography, demography, and see how their effect is on bridge deterioration and how it affects maintenances as well. So the way we collect our data is basically our primary data source, which is National Bridge Inventory. We have developed a web crawler that goes onto the Federal Highway Administration's website. We collect all the CSV files that they have hosted, and we convert them into JSON format. And while we are doing all this fetching and conversion, we also run a cleaning algorithm, more like cleaning and transformation of the data so that we get all the good data. So basically, it's basically looking for the missing values and taking it out of the records and everything. So now that we have all these 17 million, more than 17 million inspection records, we want to model bridge maintenances. We want to see the patterns that it has. So what we do is basically we go through a filtration criteria, more like categorization, not filtration. I would say more like categorizing these bridges into several different classes with respect to maintenance. So a bridge has three main components, three major components, and So looking at the data, we can figure out from over a period of time, we can look at just look by looking at the condition of these components, we can make out if these bridges were maintained from time to time. So on the right, you can see a cube, which basically represents the three main components. And so we kind of look every bridge, so every point on that in that cube is a bridge, and we try to categorize these bridges into several different classes. And once we have these different groupings, which kind of represent what kind of maintenance activity is being performed on that bridge, we run a machine learning algorithm to find influential variables and find, more importantly, find how these influential variables are interacting with each other. So what we use for our machine learning algorithm is called a decision tree, which is very intuitive and very easy to explain everybody why a maintenance was done on a particular bridge by just looking at the conditions that it satisfies according to the variables that we include. So in the next slide, this is the final slide, I am actually just including what the results looks like. So these results are basically so we have 3 heat maps and 1 heat map for every component and their maintenance. And there are a list of attributes that basically are organized in some kind of ranking, which is more relevant for the maintenances. So as we see, these this become, and it is more interactive. So basically, you can go from one state to another and see and compare. So these kind of results are very interesting for bridge engineers and decision makers, and they can test their assumptions and theories and understand more about the bridges. So this is what I do. This is what my research is. Thank you.
Thanks very much for that. I think folks who are not familiar with the bridge domain in terms of research probably can see the number of variables on your last slide there is pretty large. And so maybe in the Q&A, we can get into questions about some of the challenges that you face dealing with that many different data sources and variables. I want to shift now to Ji-Young Lee, who is from University of Nebraska Lincoln, joining us to present their research as well. Thank you for being here.
Okay. Hi, my name is Ji-Young Lee. I'm from University of Nebraska Lincoln. I'm going to present about the deep learning vision-based inspection for concrete bridge deficiencies. This is the project overview of the SMARTY project. I think many of the people in this room will be familiar with this, which builds a pipeline for the aging rural bridges from its health monitoring to analyze the social impact. And I am working on the part of the next generation health monitoring, which gather the data from the bridges and building a map for the further assessment. So this presentation will follow this order from the data acquisition, process the acquired data for stitching to build a bridge map and detect deficiencies from the collected images, such as crack, and then finally mapping and the further measurement with the created map. These images are examples of the bridges we use for this project. We gathered images from this bridge using a UAV from several bridges located in Nebraska. Thankfully, with the help from the Nebraska Department of Transportation people for the traffic control. UAV is either autonomously or manually fly over bridges with a certified remote pilot to scan the various parts of the bridges, such as bridge deck or pier, with varying bridge features, such as like bridges with patch or bridges with asphalt or sidewalk or the pedestrian bridge. We also like manually measure the crack width for the further assessment. The collected images from each waypoints and then processed for the stitching using Pix4D mapper application. This program reads the GPS coordinates from each images and analyze the image key point features to find any overlapped points to generate a whole bridge map. I have attached some of the example features from either on the side or the center of the bridges. so that we can see that there are like more matching key points on the center rather than side, which have like more overlapped images taken from the UAV for the more like precise matching result. This is the example of the generated bridge map using a Pix4D, and each of the images are stitched together to create this map. We cropped some of the unnecessary regions, such as side images with like includes grass, so that we can more focus on the bridge size rather than other natural images. Next, we process the images to feed into the deep learning model for the crack detection. Firstly, we label the images taken from UAV, not from the stitched map, to only focus on the transverse cracks, which is run perpendicular to the direction of the traffic. The image below show the example of labeled image, which like labels are highlighted as blue. The original image has size of like around 3000 by 4000, which is like very high resolution, while this image is like cropped into some of the small patches, size of the 255 by 255 to augment the data. So continue from the patch extraction, the images for the UAV is processing for generating patches from the original image data set. And those generated patches are divided into training, validation, and testing data for resulting portion with a random set. And each of the data set has like almost identical number of patches, so that each data set has a similar impact for the training result. For the training, we use the deep learning model called the Mascar-CNN, which is originally for the instance segmentation for the given input. But for this training strategy to avoid the issues with the smaller data set, we use the pre-training model with the natural image data set with the either ImageNet or COCO, which has like more than 1 million images. So for the pre-training, the train was like whole network to increase the ability for extracting the just like general image features. But the model is like fine-tuned with the only partial layers. To like learn more specific features from the cracks inside. After prediction is completed, we just like split the generated bridge map into like certain size of the cells and make prediction for it. And the prediction result from each cell is like generated for the JSON file for each cell, which contains information of each like predicted polygons and the control line, which is used for the further measurement. And based on the images I showed you before, this is the red highlighted area is the crack we found from the predicted model. And for the furtherly, we also measure the width of from the generated map based on the perpendicular distance from the predicted center line of the polygon to each crack to the control line of the JSON file. And this is one of the example of the defined crack from the whole bridge map. And this is all of the slide I have. And thank you.
Thank you very much for that. Our next presenter today is Ashley Ramsey from University of Nebraska, Omaha. Hi, Ashley.
All right, so today I have a demonstration of the data visualization project that I'm working on. And this is sort of a work alongside Akshay's work with the National Bridge Inventory. So this data set is a government survey on bridges that are longer than 20 feet made for vehicles in the United States. And each bridge has various aspects of its conditions, environment, and use documented, and this makes up the data set that Akshay uses, which is then processed, and there are condition ratings from 1 to 10 for each bridge, which corresponds to the bridge health, the bridge's health. And so we can use the the year-by-year condition ratings in order to determine when a bridge needs an intervention. Meaning a bridge intervention, in this case, meaning an instance in which a bridge receives repairs. And so what I'm doing for this project is I'm creating this heat map as a post hoc visualization of the decision tree that we use to process that information. So some of the features in this heat map include the option to sort by different kinds of bridge repairs that we see. So, for instance, this is sorting Nebraska bridge repairs by superstructure. And so we'll see, like here, this ranks latitude as the most relevant feature in, or the most relevant feature in prompting a repair of a bridge with regards to superstructure. It also has the option to display multiple states and to compare them side by side. Sorting by the average of a given feature. We also have the ability to remove certain features if you only wanted to focus on a certain subset of features. And the ability to adjust the scale that we see here. And we can also track features by selecting them here. So if they were to move around in the resorting of these features, we can kind of keep an eye on them. So the purpose of this project is to visualize the data that Akshay has in a way that allows for user interaction and exploration of the data set. So as an example scenario of an interactions, we can say that a bridge engineer wishes to compare data from Nebraska and Kansas to see which features are most relevant for prompting deck repairs. So we can select Nebraska and Kansas here and then sort by deck repairs. So here we see that latitude is the most relevant feature for these two states in prompting deck repairs. But the heat map here, maybe the bridge engineer thinks that there's a little bit too much going on here. So they can go over here and deselect some of the less relevant features. Like so. And now the heat map looks a lot cleaner, and they can adjust this and find that there are some areas where, for example, Kansas has a high average daily truck traffic, and that's the highest relevance there. But as the average between Kansas and Nebraska, the latitude is still higher. So from here, a bridge engineer could further refine or change the direction of their query in sort of an interactive and exploratory fashion. For example, they might want to add in Ohio in the visualization, and we see that the features shuffle around quite a bit. And I think that's all I have.
All right. We have one more presenter before we move into the Q&A session. That is Prashad Chetty, University of Nebraska at Omaha.
Okay, so the topic is like a population analysis approach to identify significant parameters of highway bridges. So I'm working with Dr. Hesham Ali from University of Nebraska at Omaha, along with Dr. Lotful Najar, Dr. Gandhi, and Dr. Brian Riggs. So the basic motivation behind this is why some bridges condition ratings deteriorate faster than others. Okay, because even if all the bridges start at the condition rating 9, condition rating 9 is given for excellent bridges. So even though bridges start with the same rating and they have the same age, after a certain number of years, some bridges may go to a condition rating from 9 to 8, while some bridges go to a condition rating 6. Okay, so if the bridges go to a condition rating 4 and below, 4 is called like a structurally deficient stage, like they are in very poor condition. So the motivation behind this is why some bridges still in high rating after several years, and why some bridges are going to a low rating. So that means like why some bridges deteriorate faster compared to other bridges. So what are the factors behind them? So the research question here is what input parameters are significantly enriched on the outcome condition ratings, such as substructure ratings. So to answer this research question, I am using a population analysis technique. So basically this population analysis is to conduct assessment of an individual element as it compares to a group of peers. So for example, here you see this is a correlation network of 1136 bridges. Each node is representing a particular bridge, and each edge is a relationship between these bridges. This relationship may be a time series relationship. So in a similarity network, bridges with a similar behavior are grouped into a common community. As you look at this correlation network, there are some bridges, they are in a common community. And then compare these clusters or communities with their peers to provide new insights of understanding the big data associated with the NBI data set, and then identify the significantly enriched input parameters while the network is created based on outcome parameter. So for this one, we divided the bridge parameters into two categories: input parameters and output parameters. This national bridge inventory data set has more than 600,000 bridges and with more than 100 parameters. So basically what we did is we categorized these bridges into two: input parameters and output parameters. And these NBI data set has certain parameters like material type, design type, region, etc. But it does not have any interactions. So what we did is we created new columns of data with some interactions. So for example, material type was there alone and the design type was there alone, but we created an interaction between them, like material star design. This is basically an interaction between a particular material type and a design type. So like that, we created materials with the different regions, and along with the average daily traffic and so on. And we considered these as input parameters. And we took bridge elements such as decks, superstructures, and substructures. Basically, they have condition ratings from 9 to 0. 9 means excellent bridge, 0 means it's a collapsed bridge. So we considered these parameters, decks, superstructures, and substructures, as output parameters. And basically, our intention is when a correlation network is created with the output parameters, what input parameters are significant for a group of bridges or community or cluster of bridges. So that is the basic thing. So in this population analysis pipeline, we have three methodological steps. One is data set preparation, second is population analysis, and third is validation. So in the population analysis itself, we have three main tasks: creating a similarity network or correlation network, identifying the candidate clusters using a particular clustering algorithm. So in our case, we are using Markov clustering, and then applying enrichment analysis. And as part of this enrichment analysis, we have used hypergeometric distribution. So our input matrix is going to be like this. So we have considered bridges between bridges that are constructed between 1991 and 1993. Age of each bridge is 26 years, and we considered all non-rebuilt bridges. That means their condition rating starts with 9 and goes monotonically decreasing. And even though we have taken 26 years of data, presently for our case study, we just wanted to see what is happening in the last 15 years. Because we don't want to consider the first 10 or 11 years, because most of the first 10, 11 years, no bridge is deteriorating. And most of the bridges have been maintaining their condition rating like 9. So there is no much variance. So we just want to see what is happening in the last 15 years. And as you see, this second matrix, this is a correlation matrix. So this is a time series data of 26 years. Anyways, we are considering only 15 years. In the last 15 years, what is happening? So the correlations are considered between time series data in the last 15 years between various bridges. So these are the correlations. Even for the correlation coefficient, we have considered Spearman's ranking correlation because the data is not normal. So a correlation network is created like this, and we applied a Markov clustering algorithm, and we could find like 8 candidate communities. So a candidate community or candidate cluster is defined as a cluster with a median size and above. So for these 1136 bridges, the median size of each community is like 55. So each community with 55 bridges and above is considered as a candidate community. And then the next task is like comparing each community with the rest of the community of bridges. So for example, if I consider a particular community, this one, so what I will do is I consider a particular parameter, whether this particular parameter is significantly enriched for this cluster in comparison with the rest of the clusters. So this is done using the hypergeometric distribution. So after finding the significantly enriched parameters for the 8 communities, we found that out of 8 candidate clusters, only 5 candidate clusters have at least one significant parameter. And what we did is like we found different significantly enriched parameters for different candidate clusters. So here you see, for example, like candidate cluster number 231, coastal region bridges, average daily traffic, D category means 500 and above average daily traffic. And these bridges are mostly southeast bridges. So southeast is a particular parameter that is enriched for this particular cluster of bridges. So like this, for each candidate cluster, different input parameters are significantly enriched. And after finding them, we divided these 5 candidate clusters into 2 categories. So just to categorize them like high performing bridges and low performing bridges, or in other words, fastly deteriorating clusters and slowly deteriorating clusters. So these red ones, as you see, these are below average, and these green ones are above average. It may look like this above average is like 6.96 and this below average is like 6.90. But we applied Crystal Values test and we found that they are significantly different in their average condition rating. So 6.96 is significantly different from 6.90. Okay, and some findings are like this. For example, bridges in Southeast region, after 26 years, they are at the condition rating 7.18. All the bridges started with the rating 9 and their condition rating after 26 years is 7.18. Whereas as you see in the bottom, these Northeast bridges, their condition ratings is like 6.85, and also Southern region condition rating is 6.85. So just if you generally compare these high rating bridges with the low rating bridges, we find some climatic region is playing a major role. And also, as you see, some interactions, for example, there are Northeast bridges that are made up of wood or timber. They are in the low performing bridges category. So that means Northeast bridges, we need to focus on Northeast bridges with wood or timber material. So like this, these are some of the current results. Anyways, what we are trying to do next is like we want to extrapolate these condition ratings of these cluster of bridges to see when a cluster of bridges goes to a structurally deficient status. So that means like less than or equal to 4. And also we want to generalize the results, since this is a small sample with 1136 bridges, whereas the NBA dataset has more than 600,000 bridges. So we just want to generalize the results in future. So this is about a population analysis technique where we are comparing one group of bridges with the other groups to find the significantly enriched parameters. And I would like to acknowledge my SMARTY team members, faculty from the University of Nebraska and the University of Lincoln. Thank you.
Thank you very much. Very interesting research. Thank you to all the presenters in this session. We do have just a couple minutes left for questions, if folks have those. While we're waiting for those in the chat, I'll just go ahead and ask a couple of quick ones for some of the earlier presenters. Both Akshay and Anoop, you talked about doing a lot of manual data cleaning and annotation, and we think about data science as being very focused on AI and machine learning and fancy technology, but obviously there's still a lot of manual work to be done with data sets. I'm just wondering what either of your experiences with that sort of workflow, how much have you had to do with that, even though it's federal data sets that are quite robust?
Yeah, actually that what I mentioned, like we have a lot of data, and all these data distributions are having which is known as bias also, because these biases can lead you to have some unfair models. Unfair in the sense, for example, that model can be responsible of doing wrong predictions. For example, let's say I have given an image to the model and it is having a crack, but my model is predicting like there is no cracks. So these kind of unfair situations are we can actually experiences. Since these data are biased in several terms, as I said, like there are so many weather conditions. We have winter, we have summer, we have rain. So when we actually collect the data, like let's say images, so there are so many factors. For example, spatial frequency distribution, what are the lightning conditions, naturalistic lightning conditions. So these kind of things actually create high variance inside the features. So our model used to actually extract these kind of features and use these features as the parameters to predict. So definitely we have to perform all these kind of exercises to clean up the data. And we used to generate smart data rather than just a general data. So yes, data pre-processing things are very important. So that's what I always advocate. Also, we should rather work on smart data.
Yeah, great.
And also the another point is like data labeling is also very costly because you have to manually annotate like things like I am having 40,000 or 100,000 images in my repository. You have to manually annotate those things by hand, and sometimes like just not a single annotation, it can be multiple annotations in a single image. So we as an AI researcher also should think in terms of like how we can process or how we can generate the same representation in the output by utilizing the same with the cheap data, like where we are not having all the perfect information.
Yeah, I was going to mention the sort of cheap data versus expensive data distinction that you made there. Akshay, did you want to add anything to that?
In my experience, even though we do have data from Federal Highway Agency, much of the earlier records that we saw kind of required us to hard code some of those conditions where we can check through the guides and see if the data is clean or not. So much of the earlier data is very, very inconsistent, even with the federal standards. So that data we kind of had to do some processing, but much of it was just hard coding. So it was some kind of manual removal of all these unclean data. Other than that, the challenges that we face and basically in our analysis is basically we have to integrate a lot of different data sets, especially these data sets come from all the other agencies, and they have their different formats. So it's a big challenge when you have to kind of put them all together, and they all have to be in the same format so that we can do, or the same unit, as to say if we're looking at bridges. So all this data have to be on the same level of analysis. So that's the major challenge that we face.
Very interesting. Thank you for that. We are going to have to move to our next section in a few minutes here. We'll be having at 2 o'clock Central, 3 o'clock Eastern, a panel discussion on smart and resilient communities and data science for social good, research and collaboration opportunities. I see we have at least one of our panelists for that session joining us, so that's great. I did have one other follow-up question for the presenters. The Heatmap tool that a couple of you were using looks very useful for multivariate data. Obviously, it makes a lot of sense for the federal bridge data with all the different variables in there. But is that tool available for use by folks in other disciplines, other kinds of research areas, as a sort of generalized tool to look at multivariate data?
Ashley? So as of now, we are just building the tool for our bridge data, but it is portable. I'm pretty sure that if you can add other analysis, the same kind of analysis, and the results that you see on the heat map right now are just for the bridges, but you can have other data represented in the same way too. So it is portable to other disciplines as well. But right now we are just focused on making it viable for bridge projects.
I would need to generalize the program in order for it to be widely used.
And I think that's one of the priorities that's Ashley's working on is how do we make this tool in a way that the input data can be in a predictable format, a standard format, and then other researchers can use it in a creative way rather than tied to just one domain.
Yeah, I definitely think that that's something worth pursuing, and certainly the hub community is one of those unique environments where you have researchers from different disciplines who may be looking at similar data and would benefit from having tools like that could be extended to other disciplines like that?
Great question and great suggestion. Thank you. Thank you, John.
I did have a quick follow-up for Ashley on your data. You showed bridges in 2 different states, and so I'm wondering how do you account for a bridge that may start in one state and end in another state? Does that data get double counted in the model that way?
That might be a question for Akshay. Do you know?
Hello?
Yes.
Sorry, I actually missed the question.
No worries. Yeah, I was asking about bridges that may originate in one state and terminate in another state. I'm thinking of Mississippi River bridges, for example. And so, how does the Heatmap tool account for situations where you have 2 states represented that you're comparing? Does it have the same data that it's using?
So when we look at the data, or we look at the bridges, so they come in a CSV file that is labeled for that state. So if the state considers that the bridge belongs to that particular state, we consider the bridge as belonging to that particular state. So basically, whatever is in the CSV file belonging to the state, let's say Nebraska, is in the bridge. So we don't have any understanding of bridges that originate in one state and end up in the other state. We just go by whatever is there in the data. Does that answer your question?
Yeah, got it. Yeah, thank you very much.
And the bridges also have a unique ID,
Yeah.
a unique structural ID, so it's easy to pick out where they belong.
Got it. Very good. Well, you guys are doing very interesting and very important work. It's kind of terrifying to see the number of bridges and what age and condition they are in. So thank you for all the work that you do, and thank you for being here in this session today.